axiomatic set theory. Okay, so we will be building set theory from a set of axioms, and we will see what we can do with that. Okay, so we're still not in the domain of proofs, so you will not see a lot of rigorous proofs. We will see one proof, one standard textbook like proof, but it's only next week that we will get started on proofs, and I will tell you how to write them, and you will see different types of proofs from different fields, subjects. But today we're still in the foundations. Okay. So our choice for axiomatization is the Zermelo-Fraenkel axiomatization. As I was just saying, this is something Zermelo-Fraenkel worked in the early 20th century. And there's in the foundations of mathematics, there's always an ongoing debate about the choice of axiomatization. But we choose this because this is the standard in textbooks and in teaching. So yeah. So we have the Zermelo-Fraenkel axioms, and we have another extra one, which is the axiom of choice, and we'll look at all of them. So I will guide you through each axiom. There's a list of them. I will give you some brief explanation for each of them, and we will see if there's anything to discuss. Okay. Before we start, we are making some assumptions. We're assuming what a set is, or we're just assuming that set is a thing. We're not defining sets, nor are we defining this epsilon relation. Okay. So set is something in where you can put some stuff. And this epsilon relation is a relation between two things. It's a relation between something in the set and the set itself. And the epsilon relation tells you if that thing belongs to that set or not. So if you do not know what this means, it means belongs to. It's like literally you read it as something belonging to set, or something being in the set. Okay, so we're not defining it, but I'm giving you the intuitive idea. And why are we not defining it is because the axioms that we're going to list down actually help us define it in a much more, rigorous way. Okay, so yeah, we'll rather have axioms concerning the epsilon and sets, and it is only in these axioms that those two are defined at all. Okay. So using the epsilon relation, if you just intuitively understand as something belonging to a set, then one can define a lot of operations which are very useful in any set theoretic system. Okay, so you can have not belonging to. So if you have not in X, not in Y, which means that it's a negation of X in Y. That's how we define it. X is being a subset of Y. Is defined as all the A's for which A is in X implies A is in Y, right? So this is something that you can get directly from the epsilon relation, is that if something is in X, implies the same thing is in Y as well. And if you can do that for all A's, then everything in X is actually also in Y. That means X is a subset of Y. Okay. You can also define when two sets are going to be equal. So X is going to be equal to Y if X is a subset of Y and Y is a subset of X. If both of the statements are true, then X and Y are equal sets. Okay, and so you have to kind of see a bit that this has an underline below it. So this is X can be a subset of Y, but it can also be equal to Y, right? So it's not a proper subset. So when it's a proper subset, we don't have the underline inside it. Just fix that typo.
It's a thing missing.
Yeah. Just, yeah. Okay. Yes. So X is a proper subset of Y is defined as when This doesn't work. Yeah. Yeah, when when this is true and x cannot be equal to y, you see? So a proper subset is when you have a subset, but you have a restriction against it being equal. Okay. So yeah, these are the things you can get from the epsilon relation. We're not really going into them because they are mostly better understood intuitively than rigorously. We're just assuming that the epsilon relation is something, and then we will define it rigorously as we go through the axioms. So any questions about these operations?
That's good.
Okay, so now let's get into the actual stuff for today. So we have the axioms. So we have 9 axioms, as I said. We have 8 axioms, and the last one is the axiom of choice. And we will see some stuff which pertains from those axioms. So the first one is called the axiom of extensionality. So this one says 2 sets are equal or are the same set if they have the same elements. Okay, so A is equal to B. This is supposed to be capital B. If for all x's in A, x is in B as well. And for all a's in x, B is in x as well. So everything in A is in B, and everything in B is in A. Okay, and thus all the elements are the same in both of those sets, and the two sets
sorry,
are equal.
I'm confused here. Now we have A element of X, but if A is a set and X is an element, that's odd.
Well,
I mean,
an element of a set can also be a set, right?
Right. Okay. So you're not following the convention here that sets are capital letters and elements.
No.
Everything
can be a set.
Okay. Okay.
Yeah, these things are also sets.
Right. Right. Yeah.
Yeah, everything can be a set.
Sure.
Yeah, so that's the basic axiom of extensionality, which kind of just defines, like, you know, what sets are, like, and why sets can be equal. Then we have
tilde sign.
The tilde is actually you know, similarity, or, you know, what do you say?
Okay.
Yeah. So A equals to B is the same as saying this.
Okay.
Yes. So that's the axiom of extensionality, which is basic. But then you have the axiom of regularity, and this is where you introduce something called the disjoint sets. So this axiom says every non-empty set A contains a member B such that A and B are disjoint sets. And what are disjoint sets? Disjoint sets are those sets which have nothing in common between them. There's nothing, there are no same elements between those two sets. So how you write that symbolically is you say for all x, x such that x is not the empty set, that implies there exists some y such that y is an x, and the intersection of all the x's is the null set. Okay, so what this means is that if your set is not an empty set, so that's the non-empty part, then it has to have something in there such that the intersection of that and the member is going to be the null set. So what this allows you for is it allows you for regularity. It's like, for every member, if you can have disjoint sets, you can build more and more sets there, more and more unique sets.
Right, but if you just have a set whose members themselves are not sets, then A and B, if B is a member or an element of A, then A and B can't be disjoint sets because B is not a set.
B is a set, right? It's a singleton.
I mean, it doesn't have to. Okay, this definition here says every non-empty set A. Okay, we have a non-empty set A, but that doesn't say that its members or its elements have to be sets themselves. They can be objects that aren't sets. And if it only contains elements that aren't sets, then this...
Can you give me an example of a set which doesn't have sets?
I mean, just the set of the numbers 0 and 1. They have numbers, but the elements of that set would not be defined as sets.
They are sets, right? They're the singletons. Like singleton, just the set containing 0 is a set. Just the set containing 1 is set. So you have two sets there.
Well, but there's a difference between the elements of our set. Let's say our set is M, and it contains the numbers 1 and 0. That's distinct and different from the set M prime, which consets the set only containing 0 and the set only containing 1.
Yes, they're two different sets.
Right, but so the second one, M prime, does have members or elements that are themselves sets, but the first one has elements that themselves are not sets.
Well, no. Here's the thing. So a set contains elements, right? But like when you're defining another set inside a set, you have to take some elements and create another set, right? So a set containing another set needs what you're going to use an axiom of specification, right? You need a property to say what are we picking up from the sets, right? So then only you can say what is a set and what is not. But otherwise, every singleton is a well-defined set within a set. So when we say a set A contains anything in there, you can pull it out and make it a set. So the point here is that like regardless of what A contains, you can make those things into a set and compare it with A. Okay? And this works. This works because the thing is, this is going to work only when we have other axioms. We have the axiom of pairing. If A and B are set, then exists a set which contains A and B as elements, right? But on its own, it's a bit difficult to say. So your point is basically, what about a set that doesn't have sets in there, right?
Right. Yeah. I mean, this axiom of regularity here, the way it is phrased here, if you don't say, okay, every non-empty set A members or whose elements themselves are sets, and then you just continue as here, that would make sense to me. But I don't see, and my understanding of sets is not that every element necessarily is a set. And there's actually a clear distinction between a set whose elements themselves are sets and a set whose elements themselves are, whatever. Can be a function, can be just a number, can be all sorts of things, but it doesn't necessarily, like an element of a set doesn't have to be itself a set, which seems to be the assumption in this phrasing of the axiom of regularity.
All right, I was just Wikipediaing or Google searching. It seems like in like modern set theory, everything is considered a set.
It is. I mean, that's why I
So
said.
yeah, so in which case, I get Chris's confusion, and I'm a little. This is actually like a much harder statement to digest than expected, but I don't know how to explain it. I'm sorry.
No.
All right,
it's fine.
okay, then
Yeah,
I'll just look it up.
But I think,
Thank you.
yeah, I think it's kind of like for now worth remembering that everything is a set. So maybe like we don't have to worry about like whether something inside a set is like an elemental number or like something else. Like it just within a set, there's also sets. Yada yada yada.
So
it's just for consistency, I guess.
It's not for consistency. It's just that we do not differentiate between an element which cannot be a set, right?
Okay.
So it's like if you think about it, you have a set and you have some elements in there. If you can have a well-defined collection, that's just a set. I mean, there's no restriction from there. So if you just take the singleton, that is A, let's say capital A brackets, it is a set. Then if you pull the element out and you don't have the brackets, so just A, and then you have the brackets around A. So you have the set A and you have just the element A without the brackets. Then A intersection the bracket at A is going to be the null set. Do you see that? Because A cannot be inside A, right? So they're going to be disjoint. So it sounds circular, but like if you pull out the element A and you intersect it with the set A, then that's disjoint because A cannot be inside A, and that's the definition of disjoint sets. Does that make sense?
Yeah, that in itself does make sense. Yeah, and I
Right.
just did post in the chalkboard mu thing a link that I found that basically confirms what you said, that in axiomatic set theory, you basically treat everything as a set. And in that case, it does make sense.
Right. So that's why I also said we're assuming that like things are sets and there are the relations. We're not defining what is a set and what is not. We're assuming almost all things are sets.
Cool, thank you.
Yes. Okay, no worries. Yeah, good to clear up. So that's the axiom of regularity. Then you have a very important axiom, which is called axiom schema of specification, or in other better terminology is called axiom of restricted comprehension. And this axiom is important because the first two, so if you can imagine what do the first two do? The first one kind of tells you when the sets can be equal, and the second one tells you like how does the epsilon symbol work, right? Like if you have a set, then you can always find something in there which is going to be disjoint. So that gives a very rigorous definition of how this epsilon relation works. So those are the first two axioms. But then when you get to the third axiom, you actually get into the nitty-gritties of set theory. So this axiom was included by Zermelo-Fraenkel because this axiom surpasses the Russell's paradox. So what this axiom says is that if A is a set and P of X is any property which may characterize the elements X of A, then there's a subset B of A containing those X's in A which satisfy the property P of X. Okay, so I'm going to read it again. You have a set A and you have a property P of X which applies to the elements of A, right? Now what we're saying is that there is a subset B of A, and be any subset. But what is special about this subset is that all the things inside B satisfy the property P of X. So what this allows you is that for any set, you can take a property and then you can pick out, okay, these things satisfy the property that I want from this set, and I can make a subset of those things, right? And this is called the axiom of restricted comprehension. You're restricting your comprehension, like we're specifying that this schema or this comprehension works for this restricted set of things. And I'm just going to go forward into this remark I wrote about Russell's paradox, which is what this axiom of restricted comprehension surpasses. And Russell's paradox, technically stated, says that every set theoretic system which has an unrestricted comprehension principle will lead to contradiction. So if our axiom was not restricted, if it was an unrestricted comprehension principle, then we will fall into the Russell's paradox. Okay, and what the Russell's paradox looks like in symbols, that if you have a set R which contains X, such that X is not a member of itself, then R being a member of R is equivalent to saying R is not a member of R. This is the contradiction, is that those two things cannot be true at the same time, right? So if you famously know what is the Russell's paradox, it is related to the sets containing the sets themselves. So what this schema of specification does is that it restricts how you choose things in a set. Like if you do not do that, you fall into the Russell's paradox. So how many of you have seen the Russell's paradox before in computer science or in mathematics? No one?
I think it's new to everybody.
Okay, that's fine. No worries. So if it is new, I will take the time to kind of explain it in a informal manner, because this might not make immediate sense. There are many ways to explain it, but one way to explain it is that we call a set good. Okay, so we have a property good, and we say a set is good when it is not a member of itself. Okay, that's what we say as a good set. And a set is bad when it is a member of itself. So every set must be either good or bad, right? So so now consider the plane, the xy plane, and consider the set of all squares. Now the set of squares in the plane, is it good or bad? Can someone tell me? Depending upon how I defined good and bad. That's the set of squares in a plane contains itself.
Yeah. Like you can have a big square and like a small square inside a big square.
No,
if I'm understanding correctly.
No.
Probably not.
I'm saying the set of here's the thing: the set is not itself a square in the plane. The set is not a square. The set contains squares, right? So when you're saying a square can contain another square, you're falling into the assumption that the square is a set. Set is not a square. Set contains squares, right? So the set of squares in the plane is actually a good set. It cannot contain itself. because it is a well-defined set of things which contains squares, but there is no way I can say this set which has these squares can contain itself. It is absurd to say that. But if you look at the complementary set, you know what a complementary set is. A complementary set is when you put a condition on a set, and then you look at everything that does not satisfy that condition. Okay, so we said we need squares in the plane. What if all the things that are not squares? So that's the complementary set. There's everything in the plane which is not a square. Would it be a good set or a bad set? Think about it. It's the set of things in the plane which are not a square.
I mean, that would include the sets that are not a square, which would include itself. So
right.
It would be bad.
Right? So when you're considering the set of things that are not a square, that should include the bigger set of things that is not a square, right? So here we fall into this trap of Russell. You see? So Russell.
I see.
Russell said is that if you're not specific, not restricted in your comprehension, you're going to include these sets into themselves. Okay? And then your set theoretic system will fall apart. And that's what happened for some time. So that's what the Russell's paradox is. So yeah, I'm going to confirm if people understand it or not. But if they don't, I'm going to give another example, which is also...
Another example would be nice.
Another example? Okay. Yeah, let me just get some water. So Russell's paradox is related famously to something called the barber's paradox. The barber, someone who is in the salon that cuts your hair. The barber's paradox is basically a puzzle, which is from the Russell's paradox, and it shows the impossibility of Russell's paradox. The barber's paradox says so we define what is the barber. The barber is the one who shaves all those, and those only do not shave themselves. The barber, be careful. We're mathematicians, we're not making jokes, but we're careful about the jokes. So the barber is the one who shaves those people, all of those people who do not shave themselves. So if I do not shave myself, and if my friends do not shave themselves, it's only the barber who is going to shave those people. Okay? So those are the people who will be shaved by the barber. Again, think of it like sets. So who are the people? What is the set of people that the barber shaves? Only the people who do not shave themselves. Now the question that the paradox leads to is that, does the barber shave himself? Do you see the paradox?
That's a paradox because the barber can't shave himself because he only shaves people who don't shave themselves. But if he does, then he falls into the set of people that don't shave themselves.
Exactly. That's the paradox.
Oh, very nice. Yeah, I get it.
So the thing is, no such barber can exist. There is no barber who's going to shave all those people who do not shave themselves without shaving himself. Okay. So yeah. So does the Russell paradox make more sense? It's actually a very historically known example of the barber. Yeah, there are many versions of Russell's paradox. I will put a link to a Stack Exchange page, which explains more of these. And I will also recommend a book which does deal with most of the things that we're going to do today. So there's Paul Helms's Naive Set Theory. It's not a very hardcore book, but it's a good book to start with and understand how set theory works. Okay? And it's a very famous book. So if you're interested in more knowing about how Russell's paradox works, how these axioms work, then you should consult this book.
I like the cover of this.
Yes, this is the set of things that contain themselves. Yeah.
Mm-hmm. Yeah.
Okay. So that's the Russell's paradox. And to have us not fall prey to the Russell's paradox, that's why we have this axiom, the axiom of restricted comprehension. And I think, a good way to think about the axiom of restricted comprehension along with the Russell's paradox is have the barber in your mind, right? It's like, why do I need this axiom? Is that if I don't have a specific property, then who will be the barber? Who does not shave himself, but shaves those people who do not shave themselves, right? So think about the axiom and the Russell's paradox in parallel ways so that you don't fall prey to it. It's easy to fall prey. And that's what mathematicians did for a long time. So the axiom of restricted comprehension also allows us for another thing. It allows us to define what the empty set is. Okay? And that's another important thing in set theory. Without the empty set, you can't do a lot of things in set theory. But there is something special about the empty set, is that it's a unique empty set. There is one empty set. There cannot be two empty sets, right? So there's a theorem, and it's the only theorem that we're going to prove in the standard textbook manner. And it says there is only one empty set, and we denote it by this phi, right? So this theorem is a corollary of the axiom of restricted comprehension. Now, before I go to the next page, which has the proof in a very nice way, nice manner, can someone tell me or think about how can we go about proving this? What comes in your mind about how should one prove this? Like, why empty set has to be unique? How should we do that?
Well, I would suppose that we use the condition for equality of sets that we've had before. So we can assume there are two empty sets, but then we've seen that, okay, if we have two sets and one is a subset of the other and vice versa, then they're equal. And maybe that way we can do it here. The problem is we don't have an element in there, but we will probably use sort of, what is it called, like the vacuous truth, or no, that's not the right word. Basically, if you have no element, any proposition is true for a set with no elements, or for the elements in a set that has no elements.
Yes, that's the way the proof actually works. That's the way it's written, and that's the standard way it is proven.
Oh, cool!
It is, and so
I was lucky.
Yeah, you hit the nail on the head. You hit the. Okay, maybe said it wrong, but okay. So that's how we're going to prove it. But intuitively, if you think about it, the empty set is a set which has nothing in it. So every set has to have the empty set in it, right? Can someone tell me why that is true? Why every set has to have the empty set in it? Because if you have a set which is non-empty, we assume that, then it has something in there. And if we have something, then that set can be the empty set. So you see this? So a set can have the empty set, and that can be an element of the set. So the set is not empty, actually. It contains the empty set.
Right. So it's kind of like double bracket, double bracket.
Yes.
Think about it
so there are many things you can do this way, actually. I haven't written them in the notes, actually. But you can get the set of natural numbers just by empty set. And how you do that is that, okay, you say we have a set A which contains the empty set. So you have bracket, double bracket, phi, double bracket. Okay, so that's the set A. Now you take that set and you put it inside another set. So you say B is A with this empty set. Do you see that? You have A, comma, brackets, phi. So what did you get? You have double bracket phi with single bracket phi. And you add more brackets and you get like the number of, brackets increase and the number of phi's increase. And what you get, you can count the number of phi's in there and you will get 1, 2, 3, 4, and so on. So the set containing those things is actually going to be the set of natural numbers. And you can get the set of natural numbers in this way, like just by including the empty set in one, and like you have concatenation of those.
That's pretty neat. That's actually very neat.
Right? Yes.
Yeah.
So the empty set is very important. So how we prove this, now going to the proof, is pretty simple. But this is the first time, hopefully, you're going to see a standard textbook proof. And it looks like this. So this is a direct application of the axiom of specification, whatever. So we suppose that there are two empty sets, X and X prime, just like Warsmith said. Then there's going to be an element Y in X. Can there be a Y in X? It cannot be, because X is an empty set. Y in X is false. But then Y in X implies Y is in X prime as well. It's true. And someone tell me why this is true.
Because the premise is false?
Yes. Remember? That's what we did last time. From a false premise, anything follows. Claudio falsely bet. So if Y in X is a statement which is false, this implication is actually true, right? And it is true independently of Y, whatever Y you choose. Right? If you assume that Y is in X, it is false, you can imply anything from there. So for all Y, such that Y is in X, they imply Y is in X prime too. So this actually tells us that X is a subset of X prime, right? Because for all Y, this is true. And we apply the same argument, but in different direction. Then we say Y is an X prime. If Y is an X prime, it implies Y is an X as well. Why? Because this is a false statement, and we can have the implication as true. So if Y is an X prime, that implies Y is an X, and we can do that for all Y. That implies X prime is a subset of X. So we had the operation of subset in both the directions. And if we go back to our remark originally, what we said is that X being equal to Y is defined as these two things being true at the same time. X is a subset of Y is true, Y is a subset of X is true at the same time, then X and Y are the same set. So that's what we use to say that X is equal to X prime. Okay, so you see, we defined this as a true statement. So we got to this as a true statement by using false statements, which is that Y is an element of X, which is false. That's what got us through the argument. So truths can be gotten to by false methods. So yeah, any questions about the proof? No?
Seems clear enough.
Okay, yes. So this is what a proof looks like. One thing you must notice, and I have this in my remark, is that this proof is not like the proof that we defined in the last lecture. When we defined the proof in the last lecture, it looked something like this, right? It was a proof within an axiomatic, it's a proof of a proposition within an axiomatic system, which is satisfies one of these things, right? But that's not what we did in this proof. It is not like that. And why it is not like that is that this proof is not rigorous and precise. Most standard textbook proofs that you will see, exception to Russell's proof of 1 + 1 = 2, are going to be like this. Most standard textbook proofs are going to be like this. But that's why they're not rigorous and precise. If you make a proof rigorous and precise, you have to define the set of the axiomatic system, you have to define each proposition, and you have to carefully work out this. And if you do that, this proof is going to take you 14 to 15 steps, almost. It's not going to be this long, it's going to be 2 pages almost. And as you can imagine, this will not work out for most things in mathematics, right? So pedagogically, writing rigorous and precise proofs for every mathematical statement is pedagogically impossible and acidic. Okay? So we refrain from doing that, and you should refrain from doing that too, unless you're working specifically in foundations and you need these kind of rigorousness. So that's the remark to remember, is that these proofs are not rigorous or precise. They can be made into rigorous and precise proofs, but they're not. So yeah, that was the empty set theorem and a few other things. Now we go back to our list of axioms. So you see how important this axiom alone is, and 2 big things come from there. Now the next axiom is also an important axiom. It's called the axiom of pairing. And it says, if A and B are sets, then there exists a set which contains A and B as elements. So this is actually the reason you can form a set of sets, right? So if you have 2 sets, then you can make another set which has those 2 sets as elements, right? So how you write it is that for all x, for all y, there exists some z such that x is in z and y is in z, right? So that's the axiom of pairing. Very straightforward but important axiom. Then we have something called the axiom of union, which says that for any set S, there is a set A containing every set that is a member of some member of S. Sounds a bit confusing, but what it means is that if you take a set A and you take the set containing all the elements of it, that's the union set. So this is where we define the what does it mean for the union operator to be. So what is the this top operator looks like. So what this means is that if you have a set A containing every set that is a member, some member of S, then that's also a set. And that's what we call the union set. So it's the U of A or U of S. And it is useful. So yeah, go ahead.
Oh, sorry. Is this union set different from power set?
Yes. Remember?
Okay.
What is a power set? Power set is the set of all subsets of a set.
Yes.
Right?
Yes.
But
Yes.
the
Yes.
union set is just the containing all the members.
Okay. Okay. Okay.
Right? It does not include
Yes.
all the. It does not care about the subsets. What you can do. Right? So.
Yes.
So yeah, that's the axiom of union. Very useful. Then you have something called the axiom schema of replacement. And what the axiom schema of replacement says is that if the domain of a definable function f is a set, we're going to see functions just in a minute. But if you bear with what a function is, then it says if the domain of a definable function is a set, and f of x is a set for any x in that domain, then the range of f is a subclass of a set, subject to restriction to avoid paradoxes. Now that can be confusing again, but if you know what a function is, we'll quickly go to the section on functions. And a function is basically a relation such that for each thing in a set, so you have a function going from one set to another. So for each element A in the original set A, there exists only one B such that phi of A is equal to B. Okay? And you better understand that definition well, because there is the condition of only one B. There is no other B such that phi of A will be equal to B, right? So that's the definition of a function, and a function has these terminologies. So A is called the domain of the function, B is called the codomain of the function, and phi of A, which is this is supposed to be phi, not f. Phi of A containing these B's, which the A's get mapped to, is called the image of A. Right? It is a subset of the codomain, as you can see. So this image is also called the range. Image and range are interchangeable. So what the schema of replacement is saying is that if the domain of a definable function f is a set, so that's the set A, that's the domain, and f of x is a set for any x in that domain. So if you take an x in that domain A, then f of x is a set. Makes sense. Then the range of f is the image of f, is a subclass of a set, right? Which is subject to a restriction. So what is the restriction for this range of f to be a subclass, subset? I would not go into the nitty-gritties of subclass and subset, but what would be the restriction for the range of f to be a subset of a set? It's going to be the definition of the function, right? How we define the function restricts us to where the range is going to be, right? So what this says, the schema of replacement, is that to avoid paradoxes, to avoid being loose or contradictory with our definition of what a function is, we have to make sure that the range of f is subject to a restriction. Okay? It might sound very, abstract and useless, but all of these axioms are going to be heavily used in our course when we get there. So yeah. So basically, again, just to say and repeat in usual terms, the axiom schema of replacement ensures that the image of every function is a well-defined set. That's all it does. So yeah, that's the axiom. Then we have the axiom of infinity. So the axiom of infinity goes something like this. So if we have something called S of x, and S of x is actually an abbreviation for x union with itself, union x, and x is some set. So if we do that, then there exists a set x, capital X, such that the empty set is the member of set x. That's supposed to be true. And whenever a set y is a member of x, then S of y is also a member of x. You see that? So S of x, consider it like a function. It's not a function. It's not a well-defined function. But imagine it like that. So what S takes in is that it takes in these sets x, and what it gives you it gives you the union of the set with itself. Now we say we have some another set big X, and we say that the empty set is there just to not fall into contradictions. And then we say whenever we pull something out of that big X, then we pull that out from the big X, and we put that into the S function. Then S of that set Y is also going to be in the capital X. Yes, that's what it's saying. So what this means is that, you can infinitely do this for every thing in X, and you can create an infinite set from here. Without using this, you cannot have infinite sets. See that? So this axiom ensures infinity in sets. Does that make sense? Might not. If not, then ask questions. Yeah.
In my brain, like when I compress the set, it makes sense. But if I'm trying to go up, it kind of confuses me a bit. But it's fair enough, I guess. As long as like it's kind of like looking at it in reverse, right? Where we pull out elements from capital X, and when we apply S to those elements, it's a part of X. So essentially, it helps us
right
in ensuring infinity.
Yeah. So the thing is, so this is related to how I used. So remember when I talked about axiom schema of specification, I talked about how you can construct the set of natural numbers using the empty set. But remember,
yeah, with the brackets, yeah.
But the empty set is the set of natural numbers is an infinite set. It's not a finite set. So how does the infinity work? The infinity works using this axiom, right? So what you can do is that, let me see if I can write it in chalkboard. Is that first you define, or you kind of define the encoding, which is we say 0 is equal to the empty set. Okay, so that's 0, and then we say 1 is equal to 0 union with the set 0. Okay, so that's 1, and then you can imagine what will be 2. Well, 2 is just going to be the same. 2 is going to be 1 up. Okay, that didn't work, but let's see. Yeah, 2 is just going to be 1 union the set of 1. And so if you continue like this, you're going to get 1, 2, 3, 4. And your set is going to contain more and more brackets. And the brackets eventually don't have anything in there because it's a bracket containing empty sets. But you can continue this for an infinite amount of time. You can get 1, 2, 3, 4, up until eternity. And this is how you get the set of natural numbers, which is an infinite set, right? So what we use the axiom of infinity is exactly for this. So you see this one union with the set itself is exactly what we're doing here. X union X. Okay?
Okay. Gotcha. All right.
Yes. So that's the axiom of infinity. Yeah. A lot of things can be done using that. And there are like weaker versions of this as well. But this is what we're going to see. So that axiom gives us the power to do infinite stuff. Then the last of ZF axioms, the Zermelo-Fraenkel axioms, is the axiom of power set. So it says, for any set A, there is a set called the power set of A, whose elements are all the subsets of A. Okay? So that's what we were talking earlier when Hojie mentioned about the power set. The power set is this, that for any set A, you can take all the subsets of that set, and then you can form a set. That's going to be called the power set. Now someone tell me, if a set has n elements, what will be the number of elements in the power set?
It's gotta be something with factorial.
Wasn't it 2 to the n?
2 to the n? Yeah.
2 to the n. And can someone tell me why is it 2 to the n?
Oh, I don't know.
Hold on. Oh, well, no.
It is 2 to the n, but like, just think about it. Set has n elements in there. And this is actually a problem of counting in combinatorics. If you figure out how many things can we choose from n objects, and how many times can we choose, what are our restrictions and stuff like that. And if you think about it like that,
this is like definitely a counting problem.
Yeah, and it's a very interesting counting problem.
Oh, because it's kind of like for loops, like the worst case scenario for a for loop in 2 dimensions, where you count all the n's and then you count all the like subset of n, like when you cut down like every single number separately.
Yeah, and then the way that that we kind of going back to the axiom of infinity, like when you define 0, 1, 2, in some sense we're kind of increasing the size of the set, doubling them like each time. Oh no, hold on. Yeah, I guess I'm kind of thinking of it as like there's like 2 possible choices: there exists or doesn't exist. That's where the 2 is coming from.
Let's start from the basic. So if a set A has 2 things in there, 1, 2, what is the power set?
The empty, the set containing 1, set containing 2, and set containing 1, 2.
Right. So how many things we have?
So we have 4 things total.
2 to 2, yeah.
Yes. Right. So
and then 2 to 3, then 2 to 4.
Yep. And how did we get there? What are the choices that we're making when we are defining the power set? We are
I guess the number, the n itself is like the big proponent, clearly.
Yes.
So it's like it's exponential, logarithmic, yeah.
Right. So so when we have a set with n elements in there, first we bring in the empty set, then we take each thing once. Yeah. We take all the singletons, right? So there's the singleton 1, singleton 2, singleton 3, all of those. We take those ones. So how many of those we would have? We would have n of those, right? Then we pick 2 things at once. We take the set with 2 elements in there. We have 1, 2, then 2, 3, 3, 4. How many of those would we have?
Like half of those, yeah.
No, another set of n of those, I think.
You would have n of those?
2 at a time, like two singletons at a time. That halves it. I think that should be half of the original.
Yeah, think about it. It's actually a very interesting kind of problem.
Oh, you hold one out and then you compare it to each one. Like you take one and then you go till like from 2 to n, and then you take 2 and then you go
see
from
that?
3 to
So
n, and
for
then you go with 3
each
and
element,
4.
you have n of those double sets, right? So for 1, I can do 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 up until eternity, right? So for 1, there are n such double sets. So for n of those, how many of those double sets would we have?
N
squared.
N squared.
Yeah.
Now, like, you see, so this is like getting abstract, but remember what we did. We took one thing at a time, and we got n of those. We took two things at a time, and we got n squared of those. Now we take three things at a time. How many of such things would we get?
Cubed. And then do you have to do it until n-1? And so you have to find the sum of that series and you should get to the n.
Right.
I think. I don't know how that.
Yeah, you're close.
I've always been bad at these things, so I really don't know.
This is the thing is that, counting can sound boring. If you do it, it is actually fun, and it is a good way to practice. But yeah, so this is the hint that I'm giving. I think you should try it yourself. Is that you like take certain things at once and you look at how many sets can we have, right? And you can actually prove this in many ways. You can use induction. Induction is the easiest. Use induction. If you know proof by induction, then you can use it easily. Or you can use the axiom that we saw, the axiom of infinity, and you can continue making these sets, and you'll kind of see some pattern. But yeah, otherwise you can use a purely counting way to prove this, just what we were trying to do. Okay. Yeah, another example is, another hint is, if you know binomial theorem, it is related to binomial theorem. You know, what is it? Recursive stuff. You can actually define a recursive function using this, and then use that. But yeah, there are many ways to prove this. So it's just a fun exercise problem that you can try. But I mean, we almost got the pattern. So that's the axiom of power set, and with that, we're done with the Zermelo-Fraenkel axioms, the 8 axioms, right? The 8 axioms with which you can do almost most things in set theory. But you run into problems if we do not include the 9th, which is the axiom of choice. It is the most controversial of all the axioms. So the axiom of choice says, you have a set whose members are all non-empty. So then the axiom of choice says there exists a function f from X of the union of members of X, and we've called that function choice function, such that for all y's in X, one has f of y to be in Y. Now, off the bat, this is not going to make any sense, because I mean, the function itself is very abstract. And doesn't seem to define where it's going or what it's doing. But if you look at it, it's going from X, and it's going to the union of the members of X. Okay, so it's going from X to top of X. And what it's doing is that is taking a Y from X, take a set from X, and we say f of Y. Where is going to be f of Y? F of Y is supposed to be a subset of the union of X, because that's the codomain, right? So f of Y is actually going to be in Y. Now that doesn't make much sense, because Y is an X, but Y is also in union of X, right? Because union of X contains all the members of X. But what this leads to is that it leads to a way of choosing things that are contained in the same set. So this is not making sense. So let me give you an example, a very informal example. Okay, and this is by Bertrand Russell, actually. So for any collection of pairs of shoes, we have a collection of pairs of shoes, right? That might be infinite. We allow for infinite stuff. So we have a collection of pairs of shoes. One can pick out the left shoe from each pair to obtain an appropriate collection, that is a set of shoes, right? So you have pairs of shoes that form a set, and if you pick out the left shoe from each pair, you still have a set of shoes, right? So this is exactly what the choice function is. The choice function helps you choose from the set X, and it creates a set which is also a set of shoes. So, defined more broadly, it says for an infinite collection of pairs of socks, socks of shoes, there is an obvious way to make a function that forms a set out of selecting one sock from each pair. You see that? You can make a function by selecting one sock from each pair of socks. And, that you can do that without falling prey to any paradoxes. So,
and is there any relationship between this choice function and indicator function, where indicator function, kind of loosely speaking, is kind of having one element of the output to be kind of true and the other elements to be false. So it's kind of like picking out one kind of, I don't know.
Here's the thing, this is, so let me give you another example. So shoes, socks maybe do not work. Let's go back to numbers. So here's a set. The set contains, let's say, I don't know, 3, 8, 9. That's one set. Then we have another set which contains 20, 24, 25, 39. Okay, that's another set, by the way. Yeah. Those are our sets, and we will have another set which is a much more bigger set, so that will take a while to type. So this is, let's see, it has 1, 400, 1000, 500, 489, 600, 7, 21. Okay. So these are our sets. Now what I can do is I can create a set which contains these three sets, right? So that's what the union does. Remember? So I can write, there's the set U, which has these sets in it. So just to make sure I don't mess anything up, I will copy paste. So first we include this set, then comma, then we include this set, and then we include the bigger set. So now we formed exactly what a union set is. It's a set containing all the other sets. Now, so this union is a set. So now imagine we have a set which has, you know, all these elements, and then we have a union of those elements. Now I decide to make a choice function, and the choice function, what it does is that it picks the smallest element, the smallest number in each of these sets, right? So if you look at this set, the smallest number in this set is 3, the smallest number is in this set is 20, and the smallest number in this set is 1. So 3, 20, and 1 form a set. Yes. And we can do this only if this function is a well-defined function. And the function is a well-defined function if you assume the axiom of choice. Okay, so the axiom of choice is exactly this. So what you do is you have a set of things, then you take the union of set of things, and then I say, from the union, I can actually pick certain things and still have a set. And that is what the axiom of choice allows you to do. It allows you to choose these things from the union. Okay.
Gotcha.
So until late 19th century, until some people like Dedekind, Zermelo, and those kind of people, until that time, everyone assumed that this was true. Everyone worked according to the assumption that this is the truth. They never cared about it. It was until Zermelo set down his axioms, and people said, no, this is actually another thing that you have to assume. And there is controversy, people who do not want to assume this. There are people actually who do not want to assume this. And this makes their life certainly much more terrific. Because if you do not have the choice, then, well, you cannot. So when things go infinite, so the axiom of choice is actually important when things go infinite. So when you have an infinite number of things and the union is infinite, can you always make a well-defined choice? That's what the axiom of choice gives you the opportunity to. And if you cannot do that, a lot of things in modern mathematics just break down, at least conventionally. So like, abstract algebra, in geometry, a lot of things are based on this. So like people, certainly there are people, and it's not a small number. There are a lot of people who do not want to assume this and want to work with mathematics. But that makes things harder. So there are two important versions of the axiom of choice. One is called the well-ordering principle. It says that every set is actually well-ordered. That is, the definition of well-ordering is actually difficult, but it's similar to this, that you can always choose a well-ordered set, right? And to choose that, you use the axiom of choice. And there's something else called the Zorn's lemma. So if you go to more like higher level mathematics, especially algebra, you will meet Zorn's lemma. And Zorn's lemma can either be a boon or curse depending upon how you encounter it. But the Zorn's lemma is basically the restatement of axiom of choice in terms of partially ordered sets. We're going to see them in a while. We will see them, either in a few minutes. I will kind of go through them, or we're going to see them later in the next week as we go to more proof writing stuff and how this axiom can be of use. But Zorn's lemma is so important in mathematics that is like it cannot be overstated how important it is. Almost all conventional maths textbooks assume that Zorn's lemma is true. So yeah, Zorn's lemma, well-ordering principle, and axiom of choice, they go hand in hand. And if you do not accept the axiom of choice, or you have an axiomatization of set theory which doesn't have the axiom of choice, then good luck doing math. So yeah, those were all the axioms. Those were the cool things related to the axioms. And then we have a couple of things about functions, not a lot, and we'll wrap it up for today. So any questions about Zorn's lemma or the last few axioms that we did before we get into functions?
Let's go into functions.
Cool. Okay. So yeah, I know that was quite heavy. If it was only like 9 statements, but just understanding those 9 statements is in itself a heavy thing, and that's like decades of work condensed in those 9 statements. So yeah, it's understandable if it's not immediately obvious. But what are we going to do with sets? Like, if your interests are not in foundations, you're not going to just deal with those axioms. You're going to use those axioms for something else. And to do more with those things, we define things what we can do with those sets. And one of those things we can do is we can have relations between sets. So one type of relation is a function. I already defined what a function is. I defined what kind of things go into a function, right? Now, you can have different kinds of functions, and there are precisely 3 important kinds of functions or maps that we're going to deal with. And you're going to deal with it in any field of mathematics. You will deal with surjective functions, injective functions, the special bijective functions. Okay? These 3 are very important, and it is important that you understand them once, because if you understand them once very well, they're going to treat you well for the rest of your mathematical life. Literally for the rest of mathematical life. There's nothing I can imagine in mathematics which doesn't use this basic types of functions. It's not always obvious what we're doing with those functions. So I have a cool graphic here that I made with LaTeX, which gives a very good exemplification of how surjective, injective, and bijective functions work. So here the function is actually considered to be a gun. So you have a shooter with a gun, and the function is the gun, and the bullets are the things that are coming from the domain A, the things that are coming into the function, the inputs, if you're programmatically minded, and you have bottles. Bottles are the things that the gun hits, right? So the gun is shooting bullets towards the bottles, and the bottles get hit, and the set of bottles is the codomain. Okay? Now, depending upon how the bottles get hit and how you shoot your bullets, you can have 3 types of situations. Okay? And those 3 are corresponding to the functions I mentioned: injective, surjective, and bijective. So now I'm going to give you the notes, and in those notes you'll have these paragraph long explanations. But I'm going to quickly go get you through those 3 types, and then you can take the time and go through the notes, and they're very well explained. So there's one assumption that we're making, which is the assumption that allows us to define what a function is. And if you remember, when we defined what a function is, we had the condition of only one. So phi from A to B is a relation such that there exists only one B which gets mapped from A, right? So here, in terms of guns, we have the condition that our gun hits a Coke bottle with 1 bullet. So it's like if a Coke bottle gets hit, it must be hit by 1 bullet. Okay. So what our gun does is it hits a Coke bottle with 1 bullet. The set of all Coke bottles that got hit by all the bullets we fired is the image of our function. So it's like, you have bottles lined up and you shoot the bottles, and those bottles that got hit are the elements in the range or the image of our function. And that's the f of A, right? It's everything that got hit. So let's see how we can do injectivity and surjectivity using this. So yeah, maybe I will go through much of this. It's not as long. So consider that while shooting, we make it entirely sure that 1 bullet that gets fired from my gun, it's only 1 bottle. So if I am shooting 1 bullet, it's hitting 1 bottle, right? So if we have 2 bottles, B1 and B2, that were hit by the same gun, then I'm sure that those 2 bottles are one and the same. You see that? If I found 2 bottles, B1 and B2, were hit by the same gun, then those 2 bottles are one and the same if the bullet that I fired is the same bullet. So what this leads to is that mathematically, if you have 2 things in the image that are the same, then the 2 things that they're the images of are also going to be same. So if f of x is equal to f of x prime, then that implies x is equal to x prime. And if that condition is true, then what you have is called an injective function. So an injective function is sometimes called an into function. I like to call it as an into function. Some people Americans call it as a one-to-one function. What it means is that one thing gets hit by one thing only. So if those 2 things are same, then the things that they hit are also the same, right? So such a gun is defined as injective. If 2 bottles got hit, then there must be 2 bullets that got fired. And those 2 bullets must be different, right? So what is the problem with such a gun shooter is that if he follows this, he might not be able to shoot all the bottles that we have in the codomain, right? It's like if he's hitting 1 bottle with 1 bullet, then the number of bullets might be less than the number of bottles. So, he might not be able to shoot all the bottles in the codomain. So if the number of bullets is less than the number of bottles and he hits exactly 1 bottle with 1 bullet, then obviously he's going to miss a bunch of bottles. That's the problem with that kind of gun, which is injected. Now, if we consider another case where we have another shooter who uses the gun in such a manner that he always hits every bottle in the codomain. So this shooter, he's talented enough to not miss any bottle. He shoots every bottle in there. But after a session of shooting, you're going to find that every bottle was hit and is broken. So he's always hitting each bottle. And this is the case of a surjective function. So surjective function means that everything in the domain, in the codomain, got hit. If you can find something in the codomain, it must have something in the domain which maps to it. So, there are many ways to, give examples about it. Is that, if you're in, let's say, if you're in America, you're going from, I don't know, California to Los Angeles. Okay. Wait, sorry. You're going from Los Angeles to Las Vegas. I'm messing up the cities. So if you imagine, if your Las Vegas is the codomain, that's where you're going to, and you're going from Los Angeles. So if you're going in the surjective manner, what this says is that from Las Vegas, there's always a road to Los Angeles, so that you can always come back. That's what the surjective function says, is that no matter what bottle we consider, no matter what thing in the codomain we consider, there's always something in the domain which leads to that. There's always a road back to Los Angeles. That's not the case with the injective function, because the injective function, some bottles do not get hit, right? But the thing is, the shooter also has a problem. Well, what's the problem with this shooter? That he surely is able to hit every single bottle, that he probably has tried more than one bullet on some bottles, out of which some got missed and only some of them hit the bottle. So in this case, you can imagine the shooter having a double barrel gun, something that can shoot more than one bullet at one time, because we need at least one bullet to hit. We can go for more, right? So we can have more bullets that can hit the same thing. And the shooter is wasting your bullets for sure, but he's hitting every bottle. So you can consider it as sort of bargain. The injective functions, you're saving your bullets and you're hitting one bottle with one bullet, right? But you're losing your bottles. In the surjective condition, you're hitting all the bottles, you're losing your bullets, right? So, choose the bargain. So one thing about the surjective function is that two things can be mapped to the same thing in the codomain, right? So that's why I said you can have more bullets hitting the same bottle, right? So if if you look at this mathematically, what this means is that if you have some y in the codomain, and if you're looking for what things map to y, you can have f of x map to y and f of x prime map to y, while x and x prime do not have to be equal, right? So our condition with the surjective function is that at least one thing gets mapped to y, but it can have more than one. So the same way, at least one bullet must hit the bottle for the bottle to break, but we can have more bullets hitting the same bottle. We can have more things mapped to y, but we need at least one. So that's the surjective condition, that's the injective condition. I hope the examples make sense, and I hope the examples are helpful. But if you try to imagine, those two shooters have problems. One is wasting bullets, one is wasting your bottles. So who's the perfect shooter? It's the bijective condition. So the perfect shooter is the shooter who has the ability to hit a bottle exactly with one bullet and has enough bullets to hit each and every bottle in the codomain. So the shooter does not miss any bottles, but he is also not wasting any bullets. So he is perfect in his shooting power. It's like, he's shooting one bullet and that bullet hits the bottle exactly. It does not miss, and he does not miss anything in the set of bottles, right? So that's the most special kind of shooter we can have, and he's the nicest of all shooters. And in mathematics, these sort of shooters or functions are called bijective functions. Bijective functions have one-to-one correspondence, that one thing is going to get exactly mapped to another thing, right? And you can do that for each thing in each set. So everything gets mapped and gets mapped in a nice way. So that's the bijective functions. And bijective functions are two directions, right? So you can see why it's two directional, because in one direction, you're saying, okay, each thing hits each bottle, so each bullet hits each bottle, but at the same time, the backwards argument is each bottle gets hit. So we have the injective argument, we have the surjective argument. So together, we have the bijective argument, right? So whenever in mathematics, we have to prove that a function is bijective, that's how you're going to approach. You're first going to see, is the function injective? Is each thing hitting only one thing? If it is, that's injective. Then you're going to check, is the function surjective? Is everything being hit? Well, yes. Then it's bijective. And if it's bijective, you allow for something called inverse functions. We're going to see that next time. But that's the speciality of bijective functions, that it allows for two sets to be mapped in the nicest manner possible, and everything gets mapped. Okay? So with that, we're done with functions. That was about injective functions, bijective functions, surjective functions. These are very important, as I said, and I reiterate that you should go through the examples, think about them, and think about examples of functions, mathematical functions. Is sine an injective function? Is sine a bijective function? Is logarithm an injective, bijective, or surjective function? And you can try to imagine, in which conditions it can be injective or not. And you can use the reasoning that I promoted here, and you can help yourself. Okay. So that's about it for today. We have coming a bunch of things that will be the end of our preliminaries next week, and we're going to see some more proof stuff, and then we will be set for calculus. So yeah, thank you for staying. We stayed a bit more longer today, but I hope it was helpful.
Thanks for the lecture, man.
Yes. Okay. So thank you, and we will meet next Monday. Later today or by tomorrow, I will be sending you the PSET. It will be the PSET 0, and you're going to be submitting it next Friday. Okay?
Okay.
Sounds good.
Yeah.
Yep.
So thank you, and also, sorry, we're not meeting next Monday. We're meeting this Friday. We will have a special proof writing kind of problem solving thing. So yeah, see ya this Friday. Actually, I forgot.
What time was it this Friday?
It'll be 5 p.m. UTC. Remember, Fridays are
Okay.
5 p.m.
Oh, yeah.
Thank you.
All right.
Okay. So yeah, the notes will be sent. Things will be informed to you, and we will be there on Friday.
Thanks so much.
Yes.
See you guys in a couple days.
Yes. See you.
See you.
Goodbye.